Hi. So are there any questions in the last lecture? So basically, in the last lecture, we obtained the Lagrange form of Hermite interpolating polynomial. So which is given by, so we can write the Hermite interpolating polynomial, which we denoted by, so finally we denoted it by Hn. So it is given by, so we have the data as x size and the functional evaluation at the x size and the derivative of the function at x size. Right? So we get this form of the polynomial. So we could write it as summation of yi times uix plus yi prime times vix, and I is ranging from 1 to n. And these uix and vix, these are the basis polynomials which are given by, so this is 1 minus twice of the li prime evaluated at xi times x minus xi times lix squared, and vix are given by, so this is x minus xi times lix squared, right? And for both I is varying from 1 to n. Okay. So this we called the Lagrange form of the Hermite interpolating polynomial. Right? So is it okay with everybody? All right. So again, as in the previous case, we have seen that if we want to have, we have the Lagrange interpolating polynomial, and if we increase the, suppose we have the k data points, and if we increase the one more data points, then these lix, you have to compute it all the way starting from L1 to say one more for the one more increased data points, right? So you have to compute all the LIX again. So you cannot use the computation of the LIX, which you have already done for the existing set of data points, right? So for the computational purpose, when your N is very large, using this Lagrange form is not advisable, okay? Because you have to redo everything starting from whatever the data set you have it, and then for the new data set, okay? So then we also have the this Hermite interpolating polynomial, we can write it using the divided differences. Okay, so which we call it as Newton's form of the Hermite interpolating polynomial. So let's write down what do we have as a Newton's divided difference interpolating polynomial. So let's take the set of data as, so I'm taking the set of data as, let's call it as Z1, Z2, Z3 up to Z2n. Okay, and let's write down the Newton's divided difference formula for interpolating polynomial of fx at these nodes. So what it is? So let's call it, sorry. So this is a polynomial. So we are going to write it as say Px. So what will be the Newton's form of the interpolating polynomial? At these nodes, Z1, Z2 up to Z2n, we will have it as f evaluated at Z1 plus Z minus Z1. Sorry, I'm taking the variable as x. So x minus Z1 times the first divided difference of f at Z1 plus x minus Z1, x minus Z2, the second divided difference of f at Z1, and this will go up to the last term is going to be x minus Z1, x minus Z2 up to x minus, so what will be the last term? 2n minus 1, right? Times the divided difference of f right? And what is the interpolation error if we have this as a interpolating polynomial? So the interpolation error will be fx basically have the interpolation error in terms of the divided differences, right? So what it is going to be for this set of nodes? Tell me. So this is x minus Z1 and the divided difference of f with respect to the arguments Z1, Z2 up to Z2. Right? So this is what the interpolation error we have it if we approximate the fx at these nodes using the interpolating polynomial. Right? So let's give it a equation number. So let me call this 1 and this is 2 and this is 3. So now what I'm going to do, so we know that the divided difference of the f, they make sense even when the nodes coincide, right? So we have seen a Hermite-Jacobi formula for the divided differences, which can be used in the case when the nodes are same, right? So what I'm going to do, I'm going to take the two consecutive nodes to be same, okay? You'll see in a minute that why I'm doing this. So what I'm going to do, I'm going to take Z1 and Z2 same as, I'm just going to take them same and I'm going to call them X1, okay? And then Z3 and Z4, I'm taking them to be say X2. So likewise, the last two nodes, Z2n minus 1 and Z2n, I'm going to take it as Xn. Okay. So if I do this, what is going to be my interpolating polynomial? So we will have this as f of x1 plus x minus x1, f of x1 x1 plus x minus x1 square, f of x1 x1 x2, and the last term in this summation will be x minus x1, x minus x, so x minus x1 square up to x minus xn minus 1 square, and the last term will be x minus xn times the divided difference of f with the arguments x1 x1 and this will go up to xn, xn. Okay. And what will be the interpolation error? So this is going to be fx minus p1x. This will become x minus x1 square, x minus x2 square up to x minus xn square times dividing difference of f with the arguments repeating up to xn, and then we will have x. Okay, so 3, let's call this 4, and this is as 5. So my claim is that this p1x which we have found, this is the same as, sorry, px which we have found. So this is the same as the Hermite interpolating polynomial which is given by 1. Okay. Now I'll just try to give you a little motivation that why I started with the Z1, Z2, and then what gave the idea that I should take the 2 consecutive nodes to be same. So just a little motivation. So if you try to recall, in the case of in the previous case when we were learning the Lagrange interpolation and the Newton's form of the Lagrange, the interpolating polynomial, we saw that the interpolation error was x minus x1 up to x minus xn. Suppose we have the nodes as x1, x2 up to xn. Okay, and times you had the, either you can write it in the form of the derivative of the f, or you can write it in terms of the divided differences, right? So let me write it in terms of the divided differences. So we will have it f x1, x2 up to xn and x, right? So if you observe, if you take x is equal to x, any of the nodes here, right? So then the interpolation error is 0. So that's how you can understand, because we are having these factors here, x minus x1 up to x minus xn. So if you evaluate at any of the x is equal to x size, the interpolation error is 0, right? So now here we are trying to find, in the case of the Hermite interpolating polynomial, we are trying to find a polynomial which will not just, so the interpolation error will not be just 0 when I evaluate at x size. It will also be 0 when I will differentiate it and then evaluate it at x size. This is what I want, right? So if I want my px, it should be such that the error should be 0 for at each of the xi for all I, and the derivative should also coincide at the nodes, right? So that motivates us that we have to have the factor of x minus x1 square up to x minus xn square. So the interpolation error should look something like this, right? So this, and to have this as the interpolation error, so the motivation is that, okay, you have to, if you try to see the form of the Newton's form of the interpolating polynomial, you get the error as this. You will get it as x minus z1, x minus z2, like that, right? So if I want to have the factors as x minus x1 square, x minus x2 square, like that, I have to have the 2 consecutive nodes to be same. Okay, so this is the just a motivation using the error. How can you say it? Okay. So I obtained this, but of course I have not proved that this is my Hermite interpolating polynomial. So my claim is that this polynomial which we have received, this is our Hermite this is the same as the Hermite interpolating polynomial. So let's try to prove that, or let's try to see how can we observe this. So can you tell me what we should do if you want to prove that? So we have one polynomial is sitting here, and then we already have the one form of the polynomial, and we want to prove that they both are the same. What should we do? We have used the similar arguments before also. So if we want to prove that two polynomials are the same, two interpolating, I mean, we already have one interpolating polynomial, and we say that if another polynomial is the same as this interpolating polynomial, it means that I'm telling that that polynomial itself is an interpolating polynomial, right? And if we want to show that two polynomials are the same, they both interpolate the same data, what we have to do? Then we can use if we can prove that this also interpolates the same data, what h and x interpolates, right? And if it is having the same degree, what h and x have, and then we are done. Because we know that the interpolating polynomial is unique, the Hermite interpolating polynomial, right? So we have proved the uniqueness of that in the last lecture. So to verify this, we just have to observe what is the degree of the polynomial px, right? And whether it interpolates the same data what h and x interpolates, right? So what is the degree of the px first of all? So you can see the highest, or in the case of the Newton's divided difference form, we know that the last term will tell you the degree of the polynomial, right? Because we are writing the polynomial as the sum of the, say, pk plus the rest of the term, right? So what is the degree of the px? So we have
2n minus 1, ma'am.
So this is going to be less than equal to 2n minus 1. Okay, so at most it can be 2n minus 1. And what happens if I evaluate p at xi? So we have to check whether this coincides with the f of xi for all I. This is one thing I have to check. And secondly, I have to check whether the p prime of the xi, this coincides with the f prime of the xi for all I. Right? So if I check these two things, and if it holds, then we know that the px is also our Hermite interpolating polynomial, right? And by the uniqueness, it will be the same as the h and x. So we just have to verify these two things. So what we should do, we already, if I want to check that whether px and the fx are same at the I just have to check what is happening with the interpolation error at the xi, that is px, this is equal to 0 for all x is equal to xi or not, right? This is what I have to check. And likewise, if I want to check the second property, I just have to check that f prime of the x minus p prime of the x, this is equal to 0 for all x is equal to xi or not. Right? So let's do that. So we already have the interpolation error, which is given by 5. So we have fx minus px, this equals x minus x1 square, x minus x2 square up to x minus xn square times divided difference of f with these arguments. Okay, and you can simply observe that f of xi minus p at xi, this will be 0 for all x is equal to x1, x2 up to xn. Sorry, I'm writing I here, so I should write it for all I is equal to 1, 2 up to n, because you have x minus xi sitting as a factor of the fx minus px. Okay. Now what happens to the derivative of the f and p? So let's compute what is f prime x minus p prime x. So I'm simply going to differentiate this 5. So I'm taking this as one function and this is as another function. Okay, and I'm differentiating it. So first I'm differentiating the divided differences. So we will get d by dx of plus. So I'm keeping the divided differences as it is. And then I'm differentiating this polynomial. So I will get this as factor 2 will come, and then I will have x summation. So I'm writing it all combined as a combined term. So I will have I is equal to 1 to n x minus xi, and with the x minus xi, I will get it as product of x minus xj square. J is ranging from 1 to n, and j is not equal to I. Right? Because each time we will differentiate one of the terms, and the rest of the all the terms will be remaining as it is. Right? So this is what we will get upon differentiating. And again, if you substitute x is equal to xi, you can observe that this term is anyway 0. And then here also you are having x minus xi as a factor. Right? So this will also be 0. That f prime evaluated at xi minus p prime evaluated at xi, this is equal to 0 for all I ranging from 1 to n. Okay, so that's what we have got. So we have got that f of xi that p evaluated at xi, this is the same as f of xi, and t prime evaluated at xi, this is the same as f prime of the xi for all I ranging from 1 to n, and the degree of the p is less than equal to 2n minus 1. Right? So therefore, I can directly use the uniqueness of the Hermite interpolating polynomial, or by the uniqueness property of the Hermite interpolating polynomial. We have that p2n minus 1, sorry, I have been using px only. Sorry, I used hn for that. hnx is the same as px. Okay, this means that so basically we have got these polynomials hnx and px, they both are the same. It's just that we have written them differently. Okay, so this form what we have got here, it is using the divided differences, and the initial form what we had written in the equation number 1, that is a Lagrange form of the Hermite interpolating polynomial. All right. So let's just simplify one more thing here. We have obtained the interpolation error also, right? So this is a Hermite interpolation error. So let's just try to simplify it further. So if we set, so I'm going to call this as, so let me introduce this notation psi n, which we have used before also. So which is nothing but this polynomial x minus x1, x minus x2 up to x minus xn. Then I can write the interpolation error as fx minus px, and then px is nothing but our Hermite interpolating polynomial now. So this will be x minus x1 square. Okay, let me use this polynomial directly. So this will be psi nx square times the divided difference of f evaluated at with these arguments. Okay. So now we know that there's a relation between the divided differences and the derivatives. Okay. So so the one assumption which we are carrying with always, that f is sufficiently smooth, which means that what is the smoothness we require here? So I'm assuming that f is 2n times differentiable. 2n times continuously differentiable on the smallest interval containing all the indices xi's. Okay, which you can see that why you can see clearly why I'm assuming 2n times differentiability, because I'm having this divided difference, right? And this is related to the 2nth derivative of the f. So if we use that relation between the divided differences and the derivative of the function, so this is the same as the 2nth derivative of the f evaluated at some xi divided by factorial 2n, where xi lies between, so xi, I'm writing x because it depends on the x, this in the smallest interval. Let me simply write xi itself. Okay, so this is what the Hermite interpolation error is. So now let's take one example and then try to see that how does it really work. So I'm taking a simple example. Let me just, because I just want to explain that how will you form these divided differences table when the nodes coincide. So let's take the function to be a polynomial itself. So 1 plus x raised to power 4. Okay, and we try to construct a polynomial so basically h and x, so if n is the number of nodes, this is the same as we also use the notation p2n minus 1x for this, right? So this clearly tells us that what is going to be the degree of the polynomial. So let me write that. So construct a polynomial. So I'm going to have the 3 nodes. So this is going to be p5, p5x, such that this p5 of the x will coincide with the fx at the nodes xi's, and xi's are going to be -1, 0, 1. Okay, so that is I'm going to have this is x1. Let me write this way. So I have x1 as -1, and x2 as 0, and x3 as 1. And the another property which I want is that the p5 prime at xi, so it coincides with the f prime of the xi for all I, which varies between 1 to 3. Okay, where these xi's are given by this. So if you want to use the Lagrange form of the Hermite interpolating polynomial, this is, of course, you have to just do the computation of the ui and vi, and then you have to just substitute here, right? So I'm going to use the Newton's form of the Hermite interpolating polynomial to find this polynomial. So I'm going to form the divided difference table. For the Hermite interpolation. So this is given by, so what we have to compute, let's just pay attention to the Newton's form of the Hermite interpolation. So you have to compute f of x1, x1, right? Then f of x1, x1, x2, and the next term will be f of x1, x1, x2, x2, like that, right? So we have to take, to form the divided difference table, I have to have the 2 consecutive nodes to be the same, right? Or you can look at it from this idea also, that suppose x1 is given to be something, I have to take a 2 consecutive nodes to form the divided difference table to be same, right? So that's what we are going to do here. So instead of the xi's, I will just, because zi's are distinct, so I will try to write in terms of the zi's, and then we will have the f evaluated at zi. So what we need for the zi, the two conjugative nodes to be the same, right? Z1, Z2 will be the same as x1, x1. So I will have this as -1, -1, right? So this you can treat it as Z1, Z2, and then we have a 0, 0, Z3, Z4, and then we will have Z5 and Z6, which is to be 1 and 1. Right? So which is basically the same as x1, x1, x2, x2, and x3, x3. Okay, so we can simply substitute because we already know what is fx explicitly, which is just a polynomial. So you can substitute these zi's here, and what we will get. So when we will substitute x is equal to -1, we are going to get it as 2, 2, and then when we substitute 0, so this will give me 1. And when we substitute 1, this is again going to give me 2. Okay, so now let's find the first divided differences. So what we have to take? So note that we cannot apply the standard way what we were doing before. We cannot take a difference of these and difference of these because we know that the two nodes coincide here, right? So we cannot divide by the difference of that. So we will use the Hermite-Genoke. We derived some properties from the Hermite-Genoke formula for the divided differences. That when we coincide, take all the nodes as say x0. So we got this formula, right? This is nothing but f of fn and its derivative of f evaluated at x0 divided by factorial n, right? So we are going to use this formula. So this is going to be f prime evaluated at the node which is -1 here divided by factorial 1. Okay, so f prime is already known, which is 4 times x cube. So this is going to be -4. Now this is okay. Here I can apply to compute the divided difference of f of x1, x2. This is, I can simply apply the standard formula, that is take a difference of these two, divide by the difference of the conjugative entries. So this is going to be 1 minus 2 divided by 1. So this will be -1. And then for these two entries, because they coincide again, so I will apply the Hermite-Genoke formula, so which will give me that this is going to be f prime evaluated at 1. So which is going to be sorry 0, because the node is 0 here. So this is going to be 0. And again, when we come to the next two entries, so they are different. So I can apply the standard, the difference of the two f, this minus this divided by this minus this. So this will be 1. And then for this, again, this is going to be f prime of 1. So which will be 4. Okay. Now we have found this. We can find the second divided differences. So which is going to be the difference of this divided by the 0 minus -1. So it is simply going to be 3. And for this, we will have it 0 minus 1 divided by 0 minus 1, which is 1. And this is 1 minus 0 divided by 1 minus 0, which is 1 again. And then this is 4 minus 1 divided by 1 minus 0. So this is 3. Okay. So like that, you can complete this table. So next I will have 1 minus 3 divided by 0 plus 1. So this is -2. and then 1 minus 1 divided by something. So anyways, 1 minus 1 is 0. So this is going to be 0. And then I will have 3 minus 1 divided by 1 minus 0. So this is going to be 2. Okay. So this is 0 minus minus 2. So 0 plus 2 divided by 1 minus 1. So 1 plus 1, which is 1. And 2 minus 0 divided by 1 minus 0, which is 2. Sorry, 1 minus 1. So 1 plus 1. So this will be 2 divided by 2, which is 1. Okay, and then this will be 0 because 1 minus 1 is 0. So this is the D5 of F1. Okay, so we have formed this table. Now we can simply write down the Hermite interpolating polynomial. So the Hermite interpolating polynomial so this is going to be P5 of X. So this will be, we have F at, so basically I'm going to use these entries. Right, so we'll have 2 plus X minus X1. So X1 is 1 minus 1. So X plus 1 times F of X1, so which is minus 4 plus X plus 1 square times 3. And then plus X plus 1 square, X minus 0, which is X times minus 2 plus X plus 1 square into X square times 1. And then the last term will be 0. Okay. So if you simplify this, you are going to get back the same polynomial, 1 plus X raised to power 4. Okay. Now what you can do one more exercise here. So you just take the data points to be, so let's take it to be minus 1 and x2 to be 0. Okay, so you will be able to determine a cubic polynomial using this, right? So you just find out what this P3x is going to be with this data. You take the function to be the same, fx is equal to 1 plus x raised to power 4. Okay. So is it okay so far? All right. So in the Hermite interpolation, what we have done, we basically have been given the data at the nodes xi. We know f of xi and f prime of the xi's, right? Given these information, we try to find the polynomial which will interpolate fx and its derivative. Now this, here we have just considered the first derivative, right? So you can have the same, you can pose the same question for the higher order derivative also, right? So say you want to find a polynomial px, which just not coincide with the fx at the xi's, but its derivative, say p at xi equals f of xi, p prime of the xi equals f prime of the xi, which we have already found. Now, so you can have the higher order derivative, say the second derivative. Suppose you demand such polynomials, or in fact, you can demand any of the derivative that you want px to interpolate, not just the fx, but its derivative should interpolate the corresponding derivative of the fx. So you can apply the same idea what we have learned for the Hermite interpolation. So these are called the generalized Hermite interpolation. Okay, so you use the same technique. For example, you can fix the, say you want to construct a px which will satisfy this data. I is ranging from 1 to n. Okay, just try to think about that. How will you do it? So you can try to either form the basis functions the way we have formed the ui's and the vi's, or you can try to write down the Newton's form of the interpolating polynomial and try to observe that what you have to do. Okay, so this is for you to think that how this will work out. Suppose I take the different derivatives of the function f, suppose they are known, then how will I determine the interpolating polynomial? Okay, so whatever the ideas we have learned so far, you try to use them. Okay, so now there's another class of the interpolation which is called the piecewise interpolation. So first of all, as you can see, there's a see one new word, piecewise, right? So let's first understand what do we mean by a piecewise polynomial. So we have the piecewise interpolating. Piecewise interpolation meaning we are going to find a piecewise interpolating polynomial. So let's just see what are the piecewise interpolating polynomials. So suppose we have to approximate the function fx on this interval ab. Okay. So what we are going to have, we have an underlying subdivision of this interval AB. Let's call it starting from the x0, x1, x2. Let's call it to be b to be xn. Okay, so basically we have the interval AB. I can write this as, this is a union of these intervals. So x0, x1, x1, x2 up to xn minus 1, xn. Okay, so as you can, I think, intuitively guess that when we say piecewise polynomial, piecewise interpolating polynomial, in each of these sub-intervals, we are going to have a interpolating polynomial. Okay, so how will, let's try to visualize how a piecewise linear interpolation will look. Piecewise linear interpolating polynomial is going to look. So in this interval, it is going to be linear. In this interval, it might be some different polynomial, but it is still linear. Okay, in the next interval, it can still be it can be some different linear polynomial, but it is still linear. You can have the continuity at this node, or you might not have the continuity at this node. It depends what are the conditions you're imposing, how you're choosing your the interpolation nodes inside the subintervals. Okay, so now you can have a different interpolating polynomial here. So at this point, I'm assuming the continuity at the nodes. So that's why I'm just joining it at the endpoints. So likewise, this is how your piecewise linear interpolation will look like. Okay. So this now you can extend it to the, you can have it quadratic, cubic, whichever polynomial degree you demand it. So it's just that on each of the sub-interval, it is an interpolating polynomial. Okay. So I'm just going to, so that there are various kind of piecewise interpolation, say local, global, but I will just try to give you the glimpse that how does this piecewise interpolation really works, and we are not going to go into much details of it at this point. If the time permits, then we'll take it towards the end of this course. But since these are used at various applications, so I just wanted you to understand it, that how does it really work. So let's take so usually you can have these nodes to be, the distance between these any two nodes might not be same, right? But for example, I'm going to consider these nodes to be equally spaced. Okay, so we have these subdivisions, and let's take xi to be x0 plus ih. I is varying from 0 up to n. So I think linear interpolation case is easy because if you take any subinterval xi minus 1 to xi, so if we have to find the linear interpolation in this subinterval, what we have to do, it suffices to find the two basis polynomials, right? So how the basis polynomials will look like? The basis polynomial, the first basis polynomial will look like, it will take the value 1 here and it will vanish at xi, and the another will take the value 1 here and it will vanish at this node, right? So if we call this is as so you can name it something, say vi minus 1x, and this is vix. So you will be able to write the interpolating polynomial pi x, where, so I'm in the interval xi minus 1 to xi. So in this interval, the polynomial will look like just a linear combination of vi minus 1x times, so when I substitute x is equal to xi minus 1, this will take the value 1, right? So I want it to be, say, f of xi minus 1 plus f of xi times vi of x. So this is nothing but your yi minus 1 and this is yi. So this is how the linear interpolating polynomial will look like in this subinterval. Now this will repeat in the each of the subintervals. Suppose I have I plus 1, I minus 2. So here again you will have, so it will take the value 1 here. So if I talk about this interval, so this is how it will look like, this one, and the corresponding basis function here will look like this. Okay, so these are like a head. So these are called the head functions. Okay, so in case if you learn the numerical methods for the PDEs, then you will see that these kind of interpolations are used to design the numerical methods to solve the differential equations. Okay, so the case of the linear interpolation is easy. So I'm going to consider the quadratic interpolation. Okay, this you can try to write it down yourself once I will explain how we are going to do the quadratic. So I'm going to consider this interval xi minus 1 to xi, and suppose I want to design a quadratic piecewise interpolating polynomial. Okay, and this I'm going to discuss it in the Lagrange form. So we have the subintervals as xi minus 1 to xi, and I is varying from 1 up to n. So if I want to design a quadratic interpolating polynomial, how many nodes I need? So if I talk about the interval xi minus 1 to xi, I will require 3 nodes, right? So now let's call those nodes at Zi1, because for each I you will have the same thing, right? So I'm also using the I in the subscript, Zi1, Zi2, and Zi3. Okay, now for Zi1, I'm going to take it same as xi minus 1. Okay, and this Zi3, I'm going to take it as xi. So what is going to be the interpolating polynomial, the form of this? So we can have, let's denote it by pix. So for x is in xi minus 1 to xi, It will be given by, so this is the polynomial, quadratic polynomial, which interpolates fx at zi1, zi2, and zi3, right? So we know explicitly what is the form of this polynomial. So this is going to be x minus zi2, x minus zi3 divided by zi1 minus zi2, zi1 minus zi3 times f evaluated at zi1. So likewise, you will have some quadratic polynomial multiplied by f evaluated at zi2, and then you just write down the expressions here. Okay. So this is how the PIX will look like. So for each I, your polynomial that is in the interval xi minus 2xi, it is going to be a quadratic polynomial. So if I denote ln x as the piecewise quadratic polynomial function, and let's call it Lagrange one. So how this is going to look like? So when I will restrict, so this polynomial is such that, so when I restrict this to any of the interval xi minus 1 to xi, this is going to be the same as PIX. Okay, and I is ranging from 1 to n. Okay, and on each of the subinterval, you can also find the interpolation error. So we will have fx minus ln x. This is going to be x minus zi1, x minus zi2, x minus zi3 divided by factorial 3, and the third derivative of f evaluated at some xi. And here x is again in the interval xi minus 1 to xi, and xi belongs to this interval. Okay, and if these points which we have here zi1, zi2, and zi3, if these nodes itself are equally spaced, that is, if I call, so in this case we have this is as zi1, and zi2 and zi3. So if zi1, zi2, and zi3, they are equally spaced, and let's call the distance to be, so let's denote it by delta I. So we are going to have this distance as, both are same, and let's call them to be delta I. Okay. Then what will happen? I can just get an upper bound of this error. This will be less than equal to delta I cube divided by factorial 3, maximum of this function over the interval xi minus 1 to xi. Okay, so this is how the things will look like. It's just that everything I'm doing it locally. Okay, so before we were working with the whole interval. Now I'm just on each of the subintervals, I will be having the same, whatever we have done it for the global things. Okay, so the advantage of the piecewise interpolation, as I say, that in many numerical methods you use this, but there's a reason why we use this method, because see what happens. So delta I is local to the subintervals, right? So if suppose in some of the subintervals, the derivative of the f has a see, the derivatives might have a very nice behavior in some part of the domain, and in some part of the domain, they might not have a very nice behavior. So this way, you can localize it. Whatever the bad behavior you are having for the derivatives, you can localize it to the sum of the subintervals, and then you have a choice for your delta I. You can choose your delta i's to be sufficiently small so that the error will still be manageable, so that the error does not grow very large. Okay, so this is just the intuition that why these maths like piecewise interpolation is used to design other numerical methods, because they are more flexible than the standard interpolation. All right. So this is like we have designed the Lagrange interpolation. Like the same, you can use the same idea to design the Hermite interpolation locally. So it's just that we will be working in the each of the subintervals, and what properties you need for your px, that will be determined. Suppose you want continuous, then I took my Zi1 and Zi3 to be same as the corresponding nodes. But if I take them to be strictly inside the interior to that subinterval, I'm not going to have the continuity of the polynomial of this function lnx at the nodes. Okay, so this just depends on the context that what is being asked, what is the requirement of your problem. Okay. All right, so we are not going to go into the much details in it now. So if you want further study in this, so there's a one very popular interpolating polynomial which is called the spline function, which is also very much used in many applications. Okay, so if you're interested, you can take it as a further reading in this direction. All right, so what we are going to see now is the applications of these interpolating polynomials. So the first application we will see in finding the approximate value of the integrals. So this is called the numerical integration. So let's just understand what do we do in the numerical integration, and then we will see how do we use the interpolating polynomials in there. So what we are interested, so we want to find the approximate value of these integrals. Suppose I have some function fx, and what I'm interested in computing the integral of f over the interval ab. Okay, now you'll say that, okay, if the function f is known to me, I can very well do the computation. I know how to integrate functions, right? But note that f, in some simple cases, you might be able to do it, but the fx can have any complex form, right? For example, if my fx is equal to exponential of minus x squared, you don't know how to integrate it exactly for any interval ab, right? So, or even if suppose you know that how to integrate the functions, but you will see that using the numerical methods which we are going to derive, it is very easy to compute the integrals. Of course, you will have some error, so it depends that how much error you want in your approximation, how much flexibility you are having in what purpose you are going to use this integral, the approximate value. So depending on that, if you allow some error, some approximation error in your final value which you are getting, then you can very well use the numerical methods rather than going to the explicit computation of the integrals. So this is the one reason why we will be developing the formula, because fx can have any complex form, or the computing the direct integral might be difficult at times. Okay. Second reason is that you will see that in these numerical methods which we are going to derive, you will be requiring only the values of the function at certain nodes. So like in the interpolation, we just require the values of the function at certain nodes, right? So it might happen your fx is not explicitly known. What you know is that the evaluation of the function at certain points. Okay, and using that information, I want to find an approximate value of the integral of the f. Okay, so in those cases also, these numerical methods which we are going to see in this section, these are going to be useful. Okay, so I will be denoting this quantity, that is the integral of the f over this interval, by if. Okay, and this procedure of finding the approximate value of this if, this is called the numerical integration, or there's another word which is used for it, it is quadrature. So the process of approximating the value of if, which is nothing but the integral of f over the interval ab. This is referred as numerical integration. Or numerical quadrature. There's another word used for it, which is a quadrature formulas or the numerical quadrature. Okay. So now the problem is clear that I want to find the approximate value of these integrals. Now the thing is that how we are going to do it. Okay? So that's where your interpolation is going to play a role. So we have the integral fx dx, which we want to find the approximate value for. So we know the approximation of fx by the interpolating polynomials, right? So we have learned in the numerical integration section that interpolation section that we can find an interpolating polynomial which is basically an approximation of the fx, right? So I can use this interpolating polynomial to find the approximation of the integrals. So that is, if I consider the integration of the Pn(x) over the interval a to b, this is going to be my approximation of the integrals of the fx, right? And I'm going to call this as Inx. Okay, and note that fx can have any complex form, right? But these Pn's are, if these are the interpolating polynomials, they are the polynomials, right? So the polynomials are simple functions; they can be evaluated very easily, right? So we are just going to make use of the interpolation to find the approximate value of the integrals. So let's just start with a simple case. So that is a case of n is equal to 1. So this rule which we will get, this is called the trapezoidal rule. Trapezoidal rule, I'm just not writing integration every time. Trapezoidal integration rule or integration formula, whatsoever you call it. So this rule is based on approximating fx by linear interpolating polynomial. So this rule, we basically approximate fx using linear interpolating polynomial. And we have an interval, so we want to find the approximation over this interval. So let's denote it, the x is in this way, and suppose my function fx is somewhere, looks something like this. Okay, so this linear interpolating polynomial which we will have, this will pass through the points a fa and b fa. Okay? That is, I'm going to approximate fx by this line. Okay, this is going to be my p1x, and we can write down explicitly what is p1 expression for the p1x. So which is given by So what this polynomial is going to be? Can you tell me the expression? So let's write down in the Lagrange form itself. So this is going to be b minus x divided by b minus a into f evaluated at a plus x minus a divided by b minus a f evaluated at b, right? And we also have the corresponding interpolation error. So which is fx minus p1x, and it is given by x minus a into x minus b. So let's write it down in the form of the divided differences. So I will have the divided difference of f with the arguments a, b, and x. Okay, so let's give it a equation number. So let me start with 1 again. So this is 1 and this is 2. Now, since we are interested in the approximate value of the integral, so what I will do, I will just integrate p1 over this interval ab. So the approximation is going to be I1f, which is the integral of a to b p1x dx. So let's integrate p1. So it's a linear polynomial, so you can simply integrate it. So this is a to b, b minus x. And we have this as a constant, fa divided by b minus a. And then we have fp divided by b minus a. And integration a to b, x minus a. Right? Now you can just simplify this. And finally, upon simplifying both the terms, you will get it as, so this is going to give you 1 by 2 b minus a square by 2. So we will have the rule as fa plus fb times b minus a divided by 2. Okay, so this is the first rule we have got. That you evaluate f at the two endpoints, and b minus a is nothing but the length of the interval. So length of the interval by 2 times this. Okay, let's call it 4. So this is called the, so suppose if you find the approximate value using this formula, so this rule is called the trapezoidal rule. Okay, and basically what we are doing graphically, if you see, this integral is nothing but the area of under this fx between the lines x is equal to a and x is equal to b, right? So basically, this is the area which we want to find, right? So basically what we are finding this approximate area. Basically this is the approximation of the whole area. This is what we are computing. So this reason is the approximate value, and what you have is the exact value is that by the black lines, right? So geometrically you can understand it in this way. So of course you can see clearly we have some error. You have fx and then you have p1x. So there's an error which we are committing in this approximation, right? So let's try to see what is the error in the approximation. So this is the error in trapezoidal rule. So of course, we already know what is the interpolation error. So we are going to make use of this. So we are simply going to integrate this 2. So what do we get? So we will get the integral of the f minus integral of the p1, which is nothing but the if minus I1f. And I'm going to call this as EF, okay, which is for the error. And we are having I1, so let's call the error to be E1. So which is nothing but integral a to b fx dx minus integral a to b p1x dx. Okay. Now using 2, we already know what this is. So this is going to be integral of x minus a, x minus b into divided difference of f value at the argument with the arguments a, b, and x. So this is what we got as E1f. So we want to further simplify this expression. So I'm going to use integral mean value theorem here. Can you recall what we have using the integral mean value theorem? So what is the statement of the integral mean value theorem? We have already discussed it before. I already stated it, I think, in the interpolation section. So it says that if you have a non-negative integral function, let's call it wx, and then let's say fx is a continuous function, right? And if you talk about this integral fx into wx dx, so it says that there exists a xi in the interval ab such that this integral is the same as you integrate wx and times fj, right? So this is what the integral mean value theorem is. So now you can see, if I assume the sufficient regularity for the f, that is, I'm going to need for the error, I'm going to need f to be twice continuously differentiable on the interval AB. So I can use the integral mean value theorem. So how will I apply the integral mean value theorem? Can you tell me now? I've written the statement of the integral mean value theorem.
When we take wx equal to f(abx) and fx equal to x minus a, x minus b.
Then how will you make sure that if you take w to be f of abx, how will you make sure that this is going to be non-negative? Because f can be any arbitrary function. So what happens to this function? If you try to see x minus a into b minus x, can I take this as a wx?
Yes, ma'am, it is non-negative.
So if you see, if your x is in the interval a to b, then if I take my wx to be this, then I can apply the mean value theorem to this term, x minus a into b minus x times f of abx, a to b. This is going to be some xi, ab xi, integral of a to b x minus a into b minus x, right? So it's just that I have to take a minus sign outside from here, and then I will be able to apply the integral mean value theorem. right? So if you do that, so what I will get E1f as integral a to b with minus sign x minus a b minus x dx f of a b j for some j is in the interval a b. Okay, now this you can simplify it, right? This is a quadratic polynomial. You just have to integrate over the interval a to b. So upon integrating, what we will get? So this is going to be b minus a cubed divided by 6. Okay, now you can just simplify this. And we know there's a relation between the divided differences and the derivative, right? So this term is going to be second derivative of f evaluated at some eta divided by factorial 2 for some eta is in the same interval AB. Okay, so what is the, sorry, minus sign is also there. So what is the formula we have got? So this is minus b minus a cubed divided by 12 f double prime of eta for some eta is in AB. Okay, so this is the error in the trapezoidal rule. And one direct observation which you can make from this formula is that if f is a P1 polynomial, that is if f is a linear polynomial, then what happens to this error?
0.
This is going to be 0. So the error is 0, meaning what? So this error is nothing but if minus I1f. So if this is 0, this means that if equals I1f, right? So this means that your trapezoidal rule is exact for the linear polynomial of degree less than equal to 1. So linear polynomial, or you can have it as any polynomial of degree less than equal to 1. Okay, so if the error is 0 for certain polynomial, you say that the polynomial. Okay, so let me just explain it. Suppose you have that you have integration rule, okay, and if you say that this is 0, the error x for some function is 0, which means that I have I of g is equal to I1 of g. This means that the rule is exact for g. So exact meaning there's no error. Okay, so in this case, we can observe that the trapezoidal rule is exact for the polynomial of degree less than equal to 1. Okay, so now if you see in this formula, it depends on the error depends on the b minus a. B minus a is the length of the interval. So you can observe from the picture, bigger the interval is, the larger the error you are going to commit, because f can be any function and you're approximating it by a linear polynomial, right? So the larger you might not get, and if f is if it is not a polynomial, it can be any arbitrary function. There's no way that the linear polynomial is going to approximate it in a better way in the whole domain. Okay, so the idea is that we are approximating by a linear polynomial in the whole interval, but we have already seen there's something called piecewise interpolation, right? So what if I divide this interval into a subintervals, and then in each of the subintervals I approximate it by a linear polynomial? Then of course you can even picturize it that you will get a better approximation. Suppose in this interval I am having a linear approximation, and then in the next interval is again I am having a linear interpolation. So in that case, you expect to get a better approximation than just approximating by the linear polynomial in the whole domain, right? So that the rule which we are going to derive using this piecewise interpolation idea, that is called the composite trapezoidal rule. And since we don't have enough time, so I will not start it now. So the idea, I'll just give you the idea that we have the interval AB, and instead of approximating the function by a linear interpolating a polynomial in the whole interval, I'm going to subdivide this into a subintervals. So let's call this subdivision as x0, x1, and then x1 to x2, and like that. So the last subinterval is going to be xn minus 1 to xn. Okay. And now in each of the subintervals, I will consider a approximation of a fx by linear interpolating polynomial. Okay. In a way, what we are telling that we have to approximate integral of this function over the interval AB, but I'm going to break this into, so I can break the interval AB into subintervals. So this whole interval is the same as, so this integral value is the same as if I integrate fx from x0 to x1, and then I integrate fx from x1 to x2, and this sum will be up to the integration of fx from xn minus 1 to xn. Okay, so now for each of the subintervals, so upon in the right hand side, if you see, I am having the integrals over the subintervals. So now here I'm going to approximate fx by the P1 polynomial and then simplify the things. Okay, and the formula which we will get, that is called the composite rule. Okay, so if you have any questions here, now you can ask now. I will continue from here in the next class. Okay, so I will, how's the tutorial going? I hope you guys are really solving out the problem sheets and then discussing it in the tutorial sessions. Any comments? So the problem set which I'm sending it much before the actual tutorial is happening on that tutorial sheet, right? So you all are supposed to solve those problems by your own, and whatever the difficulty you face in solving those problems, that you can discuss it in the tutorials. Okay, so it's important that you solve those problems, you try those problems by your own, so before going to the TSSM. All right. Okay, so we will stop here.